In our third module, we continue this discussion of clustering, but within the context of probabilistic model-based approaches, specifically mixture models. And we discuss how mixture models allow us to capture uncertainty in the assignment of data points to clusters. And we also motivated the use of mixture models as opposed to k-means just by describing some of the failure modes of k-means, because k-means assumes these spherically symmetric clusters and computes assignments of data points to the clusters just based off of the cluster centers. So there are a number of scenarios in which k-means just really can't capture the underlying cluster structure very well. So in our discussion of mixture models, we used a very visually appealing application of trying to group images into related classes. So for example, here we might have an unlabeled jumbled set of images that we somehow want to group into, in this case, images that are all sunset images, forest images, and cloud images. But we talked about the fact that we just have this data that's all mixed together. And a question is, how are we going to handle this? Well, in our probabilistic approach, we're going to treat the observed quantity, which we represented just as this RGB vector, as a random quantity and look at distributions on that vector. So the distribution can have a really complicated form but because it's mixing over these different classes. But to think about unjumbling this mess, we talked about introducing cluster-specific Gaussian components or possibly other distributions, though in this application we're looking at Gaussians, and then saying that our mixture model is just a weighted collection of these different components with weights based on what the relative proportions of each of these classes is in this data set. So more formally, we said that our mixture Gaussian model was defined in terms of a collection of Gaussian components, each defined with a specific mean and variance, as well as a mixture weight. So how heavily that class was going to be represented in the mixture. So all of these pictures are just for one-dimensional data, but we talked about how we think about defining mixtures of Gaussians in higher dimensions. And then we turned back to our document clustering task, where here, remember our document representation, if we think of using TF-IDF or just simply word count vectors, has a representation that has dimension equal to capital V, the number of words in our vocabulary. So we talked about some of the challenges of scaling our mixture models to these high dimensional scenarios. And in particular, instead of allowing arbitrary Gaussian components in the mixture model, we said that in practice, one would often want to specify just a diagonal form to the Gaussian covariance matrix to dramatically reduce the number of parameters. But we said that this form is still much more flexible than what you have in k-means, and in particular, we're still going to be learning the weightings on these different dimensions in our mixture Gaussian model. And then, having specified our mixture Gaussian model, so understanding the components of this probabilistic model, we turn to how to do inference in this model. So remember, we're just going to present the algorithm with a data set, so a set of points that are unlabeled, and we discussed an algorithm in particular called expectation maximization, or the EM algorithm, that allows us to jointly infer both the model parameters as well as these soft assignments that describe our uncertainty in the assignment of data points to specific clusters. So in particular, this EM algorithm is an iterative algorithm where the first step, which is the E step, forms these soft assignments based on our current estimate of the model parameters. Then the second step, which is called the M step, computes the maximum likelihood estimate of our model parameters given the soft assignments at the current iteration. And then we iterate again and again and again between these steps until convergence. And just like k-means, we show that EM can be described as a coordinate descent algorithm. So we get the same types of properties where you get convergence to a local mode of the objective. So like k-means, initialization matters a lot. And typically people rerun the algorithm many times and choose the best solution. But another thing that we described was that for our mixture models, we have a lot more parameters than we do for k-means. But we presented some ways to think about handling or at least ameliorating these issues of overfitting. Okay, well, in pictures, we presented a set of illustrations showing EM in practice, where over iterations of the EM steps, we see how we're able to learn soft assignments of observations to specific clusters, as well as the cluster parameters, where even at convergence of the algorithm, we can still get these uncertainties in whether a given data point is assigned to one cluster versus another cluster. And this is actually something we want. We want these uncertainties as part of the output of this algorithm. And finally, at the end of the third module, we related very formally the expectation maximization algorithm for mixtures of Gaussians to k-means. In particular, we said if we look at a mixture of Gaussians with spherically symmetric Gaussians, so diagonal covariance with same elements along the diagonal, and then we shrink that variance to 0, and we run our EM algorithm, the output is exactly the same as k-means, because what we're going to end up doing are making hard assignments of data points to specific clusters just based on the distance to the cluster center. So indeed, looking at EM for mixtures of Gaussians is really a generalization of the k-means algorithm.